Thank you. As Jonathan said, I'm Magnus Hagander. I work for a consulting company in the Nordics called Replication and Clustering. So I'm from Stockholm, Sweden, myself. I may be the furthest away speaker this time, I think, because I don't think we have a number of people here from India and Pakistan and those places, but I don't think any of them are speaking. But I may be wrong.
What about France?
Sorry?
What about France?
Let's just say I'm from far away. There are probably others who are there. So I'm going to talk to you about Postgres backup strategies. And let's start by sort of the interesting arguments that I hear sometimes that we're not going to talk about is, for example, but I have replication, I don't need backups, right? Because I have a second node if my first node dies. Or maybe I even have multiple nodes. So I can obviously not have a problem, right, as long as I have that, particularly if I run it in the cloud. I'd like to say if you run a multi-node system with multiple replicas all in the cloud, then if any time, that's when you need your backups. And replication is definitely not a substitute for backups. There are many scenarios where this simply will not be enough, right? And the same goes for clustering. People say, well, I have a clustered server running on whatever, Red Hat cluster, Veritas cluster, or anything. It does not solve the same problem that backups does. You probably need both of them, but you can't get away without the backups in pretty much any scenario. Or another classic that I've seen, my SAN is 100% uptime. I have a guarantee from my vendor. Yeah, good luck with that. We actually had a fairly well-publicized instance back in Sweden about a year ago when one of the three largest sort of outsourcing/hosting companies had a tiny little failure on their SAN. They had one of these 100% guaranteed uptime SANs, replicating synchronously to multiple locations, and everything was all fine, until there was a tiny little software error in the SAN, which replicated the corruption really rapidly across all locations, and they lost something in the order of 5,000 virtual machines running their customer systems at once. It took them, as far as I know, several months to get everything back, because they were also running a backup system that wasn't actually supported on the version of Windows that they were running. Which goes to say, backups are actually quite important, even if you have 100% guaranteed uptime, whatever, because there is no such thing as 100% guaranteed uptime anything. It just doesn't exist. So talking a little bit about more on the strategy side, a lot of people tend to remember to think about backup planning, right? We know all this stuff. We remember, how often do we take our backups? How much retention do we need? Like, how far back in time do we need to look at backups? What granularity do we need, particularly far back in time? What kind of performance impacts do the backups make on our system when we run them? Because all of these are obviously non-zero numbers. But there's probably something that's more important, and that I see in a lot of places that have very good plans for backups, is that you forget to do your restore planning. And that's probably even more important in a lot of cases. It doesn't actually matter in most cases how long it takes to take your backup, as long as it's not longer than your backup interval. So if you're taking a backup every day, it is a problem once it takes more than 24 hours to take the backup, because you're in a situation that will never end. But once you need to restore, that's usually your time-critical operation. Okay, once the system is down and you need to restore, people want it back up in seconds, preferably, which is why we have clustering and replication to solve those problems. But if it takes you, several days to restore from backup, or again, in the case of this Swedish provider, several months to restore everything, that's probably not acceptable. And this is actually a lot more important, which is why we have these multi-stage. So we may have a cluster that takes care of hardware failure and failover with zero data loss within seconds. Then we might have an asynchronous replication to a different data center that will take care of the next class of problem, and where we have a potential data loss of maybe a second or two and a little bit longer time to deal with failover. And then we keep layering, and in the end we come to our backups, which will take longer. Right? We will have downtime when we restore from backups. That's the way it works. But we will hopefully have a manageable downtime and never actually have to use it. Right? It's the last resort, but when someone, your DBA goes in and didn't have his coffee in the morning and drops the wrong database or the wrong table, no replication is ever going to save you. Well, I guess in theory, in the case of Postgres, our old style Slowney replication will actually save you because replication will stop working when you do that. But if you're using the new integrated replication, it'll happily replicate your drop and you will lose all your data. That's when we do need to use the backups. So when talking about backups in Postgres, we have sort of two major ways that we can split this up. And I'm sure, I assume, is there anyone in here who has never actually done any kind of a backup on a Postgres system ever? Good for you. We have two major classes of backups that we can do in Postgres. We can do the logical backups, which is what, it's centered around the tool PGDump, which I'm sure, who has used PGDump? Interestingly, there are people in here who have taken backups and never used PGDump. That surprised me. The other option we have is physical backups, which can be done in several different ways. We can use file system snapshots. We can use the new tool that came in Postgres 9.1 called PG-based backup. We can do manual-based backups. There are a number of different ways that we can do these, but there are sort of two fundamental groups, the logical and the physical backups. The logical backups are what most people sort of start from when you start small, or when you're not coming from the Oracle or Microsoft or DB2 world. People tend to start with PGDump, with the logical backups. And this is basically, a logical backup is an SQL script containing your database schema, all your create table, create index, create function, whatever, just the statements, and your data. In the case of PGDump, it'll be a tab-separated copy data of all your data just into one big script, in theory. The logical backups are restored through simple SQL commands because they are simple SQL commands. This gives you a great amount of flexibility because you can go in and actually edit your backups before you restore them if you want to. Rename columns, rename tables, delete parts of your backups before you restore them. This is all doable. But it's not the greatest when it comes to performance. As in, there are a lot, once you get to a certain size, you simply can't use PGDump for your backups anymore. But once you reach that point, it is a very flexible way of doing it. And it gets you pretty far.
Was parallel PGDump committed to 9.2?
No. It's on the ability to run parallel backups is in the queue for the next commit fest for 9.3. So when you're dealing logical backups, again, PGDump is your main tool. There is another tool. This is the one you want to be using. PGDump dumps a single database. So if you have multiple databases, you have to run PGDump multiple times. Right? 100 databases, 100 PGDumps. It runs over a regular Postgres connection, meaning you can run it anywhere. You log in with a regular user. Well, preferably it'll be a super user to be able to actually access all your data. And what PGDump does is it guarantees a consistent snapshot across your data. And this is why it is currently single-threaded. So what happens is basically when PGDump starts, it opens a transaction in your database. And then using the MVCC isolation system in Postgres, it'll just keep this transaction running for the entire dump. And it'll copy all your data out. And the MVCC system guarantees that the dump will be consistent. So that if you delete and insert and update data while your backup is running, we're just not going to see it. We're not going to see any changes that happens in the system after the PGDump starts. But by not seeing those, we know that the dump that we created can actually be restored. If you have a non-transactionally consistent dump, in theory, say someone inserted or removed data, for example, between two tables that had a foreign key, you might not be able to restore your data. That's why it's very important that PGDump creates a consistent snapshot. And that is why it's currently single-threaded, meaning that it'll run over a single connection, it'll dump one thing at a time. As Jonathan mentioned, there is work being done to have a parallel PGDump so that we can dump multiple tables at the same time while maintaining transactional consistency. You can do this today. You can dump multiple tables at the same time by simply running PGDump, telling it to dump just this table and then dump just this table. But then you don't get guaranteed transactional consistency So you're not guaranteed that your backup will restore. Now, if you know your environment, you can say, well, I know that nobody's going to do this, so I know that this is safe. And then you can do that using external tool that will invoke multiple copies of PGDump. But it can't be sort of generically guaranteed if you're running multiple PGDumps. It's also, as I said, you run PGDump once on each database. So if you're dumping multiple databases, those dumps will not be transactionally consistent. But Postgres doesn't support cross-database transactions anyway. So that's actually not giving up anything. Yes? Oh, yeah. No, absolutely. You can kind of fake it, but the problem there is that then your application is frozen while you're running your backups. Yes. Oh, yeah. Yeah. Right, right. You freeze all data, you freeze all activity, you make sure there are no open transactions, and then you open 100 parallel transactions. Then they will see the same snapshot. Yes. You must make sure, though, that I'm not actually sure exactly how freezing works in PGPool, but if it has an open transaction and you freeze it in the open transaction, it's not going to work. You need to make sure there are no open transactions. Yeah. So yeah, there are ways to do that. It's kind of hacky, which is why actually Postgres 9.2 has what's called snapshot exporting, which is the foundation that required so you can actually have two connections working in the same transaction or with the same snapshot. But it doesn't have the parallel PGDump yet. We will probably have that in 9.3 as the code is there. It just needs to be reviewed and applied. Unfortunately, 9.3 is a year away. But there's always something in the next version, right? That's what everybody tells you. Oh, you want that feature? It'll be in the next version. The mythical next version. So PGDump supports a number of different formats in its output. There's 4 of them, actually. The default is that it uses something called plain, which is just a big SQL script that's sequential and nothing else. Don't use this. You should always use the custom format, which is set by running -F and then lowercase c. And this is an indexed format that's basically, it's in the end, it's still the same. It has the plain text SQL inside it, but it has an index so that when we restore this, we can rapidly find different parts, we can do filtering, we can do all sorts of advanced things with our backups. If you have an SQL script, well, have you tried loading a terabyte SQL file into your favorite editor? I mean, whether it's Emacs or VI, it's not going to be pretty. It doesn't really work that way. So always use the custom format. It will also be compressed by default, unlike the others. But that's something you can turn on or turn off. And when you're doing backups, make sure that you always dump the whole database. Right? As I said, it does support dumping individual tables, individual functions, individual everything. But if you do that, you don't get the transactional consistency. And if you don't get the transactional consistency, it's not really useful for backups. Now, we use PGDump for a lot of other things than just backups, like transferring data to staging systems or things like that, in which case it might be perfectly fine to do individual objects. But if you're doing backups, you want to do the whole database at all points.
The custom format also supports the statistical tables, too.
The statistical table? Yeah.
When you run analyze and you
Oh, you mean, yeah, okay, it can store table statistics. Yeah, yeah. So, yeah, basically, custom format is what you always want to use. There is also actual support for tar format, which is sort of like, it sounds neat because then you can use any other tool that speaks tar, but really, don't go there. The tar format doesn't add anything that custom doesn't, but it gives you some drawbacks. So this sort of, yeah, it's a standard format, doesn't really help you. But the main thing here is avoid the default that is plain text is not good for backups. It's good for other things like extracting schemas and things like that, but it's not good for backups. For backups, custom format and full database. So running PGDump on your system, when you do that, will obviously have an impact on your queries, on what your application is doing. It doesn't block any queries. Right? It's not like some databases whose name shall not be mentioned, where when you ran the dump, it would actually, you'd stop the database for queries. You'd run the dump, and then it would run queries again. You really don't want that. What PGDump does to extract the data is it runs standard copy commands. The same commands that you can run yourself, the same commands you can run from PSQL or using PGAdmin to extract data. It runs the same thing, and it uses a single backend. Because remember, it was single-threaded on the front end. That means we have a backend on the backend. That's how Postgres works. And it just dumps data as quickly as it can. Now, Postgres has a feature, though, whereby when it detects that you're doing a big sequential scan, it'll prevent PGDump from exhausting your Postgres buffer cache. It'll restrict it to a smaller number of buffers and just go around in those, which reduces the impact on the rest of the system. Because otherwise, a PGDump would be a pretty good way of killing your cache in the system, because it'll read everything that's in your database. So it uses the ring buffer strategy that's in there for any kinds of larger sequential scans, which is obviously what copy does. However, it may well ruin your file system level cache, because we're reading all the files through the file system. It kind of depends on exactly how smart your file system cache is. Some file system caches will, in some cases, detect that you're doing this and try not to get it completely clobbered, but they don't know as much about the scan as Postgres does. Postgres can very easily identify this for its own buffer cache, but we can't for the file system cache. And we definitely can't for your hardware cache that sits on the RAID controller or the SAN. We can't reach those. So that's obviously, it is going to cause I/O on your system. It's probably not going to cause cache issues. But if your database is big, we're going to read it all. We will only read the tables. We don't actually read the indexes, but it's probably going to generate a bunch of I/O. And something you might forget is that obviously writing the dump file causes I/O and causes quite a lot of I/O. So avoid putting the dump file on the same disk that you keep your database on. Like even if it's, I see a lot of people, we do a temporary PGDump there, and then we send it off across the network. So suddenly you're also generating writes on the same drive that we're already generating reads on. So they'll be fighting for the same resources. So make sure you dump the file, if you have a lot of data, to a different disk, whether local or across the network or something like that, but avoid dumping it on the same drive that you have your data on it. Because it's fundamentally very different I/O patterns, and it'll just sort of kill the hardware's ability to streamline the access. So that will cause increased load. We also have support for compression in PGDump. And what's worth noticing here is that compression in PGDump happens in PGDump. It does not happen in the Postgres backend that PGDump connects to. So the data being transferred from Postgres to PGDump will be uncompressed, and then it will be compressed and written to disk. And this is actually a pretty efficient way of throttling I/O as well, if you want. Typically, when you enable compression, I think the default level is whatever libz has as the default level, which I think is usually 6 or 7. On most systems, setting the compression ratio to 3 or 5, it has one of these typical switches like your gzip, 1 to 9, how much compression do you want? Usually somewhere between 3 and 5 is where you have the breakpoint where you'll get the fastest running backups. If you compress more than that, then the system will bottleneck on that it takes too long to compress. And if you set it less than that, the system will bottleneck on I/O. But we can use this because in a lot of cases when we're running this on the production system, I/O is our problem, right? So if we set the compression higher, we make the backup CPU bound. That will slow down the I/O because the receiving end can't keep up. It will make the total time of the backup take a bit longer, but it will make a lower load impact on the system because you're leaving some I/O capacity for the running system as well. And likewise, you can drop it lower if your system is CPU starved. But a database server today is very seldom CPU starved. It's typically IO starved. That's where your problem is usually showing up. Yes? Yes. Oh, PGDump is single-threaded. So it will only ever use one CPU. So if you enable, say, compression level 9, then that one CPU will peg at 100% running the PGDump compression. And the backend will sit running maybe 20% of capacity feeding it data, because we're pegged at 100% CPU there. So that's good for backups, probably, because with backups, it's more important that you don't impact your running operation than that the backup finishes 5 minutes. This is also interesting is in where you run PGDump, because PGDump is a regular Postgres client, so you don't actually have to run PGDump on the database server. If you run it on a separate server, remember that the compressions happens between PGDump and the disk, so that the data that gets sent across the network is not compressed. So there are interesting ways to do this if you want the compression to happen on the database server. The typical way you'll see that is you run something through SSH, right? Command I see a lot is, you SSH into your database server, you run pgdump, -z9, that's the maximum compression level, custom format, because we said that use user Postgres dump the database. By default, it'll spit it to standard output, and you can write it to disk on your client with the compression happening on the server. Now, if you do this, this is probably a good idea to add. Turn off SSH compression. Depending on how your SSH is installed, compression might be on by default, in which case you're trying to compress the data twice, and that will just waste your CPU. So if you are running your pgdump tunneled through SSH, turn off compression in SSH, use the compression in pgdump. That's the better way to do it. And don't do both of them. That just creates unnecessary overhead. When we're restoring from a pgdump, we use a command called pgrestore. Now, if you run the dump in plain text mode, we just use PSQL, the standard command line tool, right? But we just said don't run the backups in plain text mode. Run them in custom format, so we use pgrestore. In its simplest form, pgrestore will read these custom format dumps, speak over a standard Postgres connection, a single connection to a single database, and restore all your data into this database. Since pgdump dumped a single database, it makes sense that pgrestore would restore a single database. It doesn't support restoring multiple databases, but you can't have multiple databases in the same dump anyway. And we can use this both for full database restores, which will be the default, but you can also pick and choose. So you can use pgrestore, pointing it at your full backup, and say, but I only want to restore this one table, or this one index, or just the schema and not the data, or just the data and not the schema, and these kinds of things. And that's where the real win comes of using the custom format dump. Because if you have a plain text format dump and want to restore a single table, it really is open up the dump file in your favorite editor and delete everything else, and then try to restore it. Whereas with pgrestore, you just say, restore this one table, and let's do it. So what pgrestore does is it runs a regular copy. Runs the copy process backwards. Okay, the dump contained the data in a tab-separated format. Well, we'll just read it back in with copy. That's pretty fast. Once we've done that, we run normal create index statements to recreate all your indexes. And then we run add constraint statements to add all your constraints. And this takes forever. Because again, by default, single-threaded. Single-threadedly, creating indexes over hundreds of gigabytes or terabytes of data will take much longer than acceptable in most cases. For a small database, it's perfectly fine. But if your database is large, it will be very, very slow. So there are a couple of things that we can do around this. A very useful flag to make your restore faster without costing anything extra is using the -1 flag when you restore. In this case, pgrestore will simply wrap the whole restore in a single transaction. It'll run begin, then it'll restore everything, and then it'll run commit. This enables Postgres to do a number of optimizations. Like it turns off, if you're not using transaction log archiving for the physical kinds of backups, it turns off a number of things that don't need to be written to the transaction log, makes things a lot faster. It has an additional benefit, which is in case your restore job crashes, well, the transaction will automatically roll back because it's a standard Postgres transaction. You don't get a half-restored database. But if you do need actual good performance on your restores, well, or actually very well improved performance, we have something called parallel PG restore. This was added, I believe, in Postgres 8.4, so it's been around for a while now. So we are able to do a parallel restore. We're not able to do a parallel backup yet. But again, restore is the point where we're usually more time constrained when we need to do it. And it works like many other tools that let you do parallel things. -J, add a number. That's the maximum number of parallel sessions we'll run. So you can say -J8, then we'll run 8 parallel restores. Each of these 8 sessions then will have its own connection to the Postgres server, meaning we will have 8 different Postgres backends that will then scale across 8 CPUs, hopefully. Now we're still dumping a single object in a single session. So if your database is one huge 1 terabyte table, and then 400 tables of 10 rows each, it's not really going to help you, because we're going to run through those hundreds of small tables really quickly, and we still have a single session that's restoring the huge table. But if you have a database that has sort of a relatively even load, it will scale, and in a lot of cases, it'll actually scale linearly. Add a -J8, it'll actually go 8 times faster. So it will try to do that. Now, unfortunately, it's not compatible with -1. So you can't use both of these. And in most cases, I don't think I've come across a single case really where, except this huge 1 terabyte table and lots of small tables, which is, I don't come across that very often. -J will be faster. It makes you give up the advantage that you had that if the restore process crashes and you use -J, then you will have a half-restored database. So you'll need to wipe the database and try again. But again, we're doing this in order to be sure to restore really quickly, so that's probably a price we can pay. The final thing we can do to make our restore performance go faster, and this does make it go much faster, but it's sort of dangerous, that is turn off FSync. Okay, you've probably all heard the advice is never ever turn off FSync, right? Because if you turn off FSync, your database may well be corrupt. And it may, which means that what you can do is you can turn off FSync, but don't forget to turn it back on. I've seen that far too many times, where people have turned it off, done the restore, forgot to turn it back on, and then realized that a couple of weeks later. So make sure you actually remember to turn it on. And when you turn it on, it's not enough to just restart Postgres with the new FSync setting. You need to make sure that you flush all the caches in your operating system. You need to get rid of the file system cache in the operating system. You need to get rid of the hardware cache in your RAID controller, unless it's battery backed. Usually, I'll just recommend, once you turn FSync on, reboot the machine. It's pretty quickly, and you know that all the caches are flushed. You didn't forget one. Because normally you do this, to save maybe hours on your restore time. Paying the 1 minute to reboot the machine, probably worth it to make sure you do that. If you don't do that, you can get silent corruption in your database. Like, it's not like we're going to start the database up next time and say, oh, sorry, your database is corrupt, restore again. You may never know until it starts crashing a couple of weeks down the road with strange memory pointers and bad data and all that stuff. So if you do this, make very sure about the second part. Do not forget to turn it back on. And if you are doing this, one thing that I've seen a lot of people miss when you're using PGDump for backups, which is, remember we said PGDump dumps a single database? There are objects in Postgres that are not in a database. Users, groups, table spaces, all of these things don't actually live inside a database. So PGDump cannot dump these objects. For this, we use the tool PGDump all, which is actually the main use, or the full use of PGDump all, is to dump all your databases as a single backup. But PGDump all only supports plain text format. And we said we wanted to use custom format, so we really don't want to be using this one. But when we're using PGDump to dump our databases, we need to use PGDump all with a -g flag, which will then dump only the global objects. And this will be a plain text SQL script, yes. But that's probably not an issue because it's small. You don't have tens of millions of users, hopefully. At least not in your database, they'll be in your web app. So run PGDump all with -g. Now these are the easiest backups, and really, in a lot of cases, if PGDump solves your problem, if it is enough, just use that. It gets you pretty far. But most of us are going to end up, in one way or another, using the physical backups. Because, in particular, they can add features, and then they can make our restores much, much faster. So basically what we have in Postgres, it stores all its databases in files. Okay? It's not like Oracle, who likes to store it in raw partitions or anything like that. It's just files. And we can back up these files. They're just binary files. We don't need to parse them. We don't need to query anything. We don't need to recreate indexes. We can just copy them. This will be faster. This will pretty much always be faster. But there are a number of restrictions. For example, they are architecture dependent. You cannot restore a dump from an Intel system onto a Spark system. Will not work. 32-bit to 64-bit will not work. Versions, you can't take a 9.1 dump, a 9.1 physical backup, restore it on 9.2. Will not work. If you've changed compile flags, if you're building Postgres from source, it may not work. And now if you're installing from a packaging system, they will usually make sure to use the same flags every time. But if the same flags weren't used, you won't be able to restore it. Your paths must be identical. You can't restore the database to a different location on the machine, or a different machine that might not have the file systems mounted the same way. It doesn't work. So it's a lot more strict about what you can and cannot do. And it can also only do full cluster backups. So with PGDump, we could do a table or a single database. In a physical backup, we do everything. If you have 100 databases, the backup will be of 100 databases. You can't make a backup of one and then restore one. Certainly not a table. It's all or nothing. Now, there are a number of ways that we can do the physical backups. The absolutely easiest one is to just do it offline. Okay? Stop Postgres, take backup, start Postgres. If you do this, we don't care how you do your backups. In any way that you can put these files back will be fine. Using tar, using copy, using file system snapshots, using anything you can think of, it will just work. Now, in most environments, this is not going to be acceptable, right? Because the whole stop Postgres step is kind of unacceptable. But in a fair number of environments, they can say, well, it's going to be down for 5 seconds because I'm doing a file system snapshot. That might actually be acceptable. And if you do it this way, it's actually pretty hard to get it wrong. And that's a good feature in a backup way. So don't forget that it is an option, but it's probably not going to be an option that works well in production. Another fairly simple way of dealing with this is using simple snapshot-based backup. Right? If your file system or your SAN supports doing snapshots of the file system, that'll just work. If you can guarantee that the snapshot is atomic across all table spaces and the PGX log directory. So if you're putting these on different disks, the snapshot needs to be consistent across the multiple disks. Almost all implementations are not. Right? If you're using things like LVM snapshots on Linux, does not guarantee atomic snapshots between multiple devices. Now, if your entire database is on a single partition, then yes, it will guarantee just that. So if your database, including the transaction log, is on a single partition, you can just use LVM snapshot, ZFS snapshots, SAN level snapshots. Some enterprise SANs will let you do atomic snapshots across multiple devices, but they'll usually make you pay a lot extra for that feature. But if you cannot guarantee it, if you cannot guarantee an atomic snapshot across all of them, then you can't use this method. You can still shut down the database, take the snapshots, turn it back on, but Again, we didn't want that. So the full way of doing it is using online-based backups, as we call it. This is basically a file system level backups while removing the constraints that I just listed. We no longer need to do it atomic. We no longer need to do all these things. It gives us something that's recoverable in combination with the transaction log. So it's suddenly more complicated to take them. It's more complicated to make the restores, but it'll give us a lot of more features. This is supported with or without archive logging. In most cases, you will want archive logging. And if you do archive logging, it lets you do the holy grail of database backup, which is point-in-time recovery, or usually written as PITR, which means that you can restore the database not just to when you took the backup, but to any point in time. But if we don't need to do that, like if we just want the 11 o'clock last night level backup, that's actually enough for a lot of people, then it's very easy to do this. Now, we can do the online-based backup in an easy way, starting with Postgres 9.1. And it uses the Postgres replication protocol. So it's built on top of the streaming replication system. We have a way to do backups. So in order to do that, you need to enable replication in your system. You need to set your WAL level to archive. This makes sure that we generate enough transaction log information to be able to restore from what's actually an inconsistent backup. And you need to set something called max WAL senders to something that tells you how many replication connections does my system allow. And since we're using replication, well, we need replication connections. If you're already using the system for replication, using streaming replication, you just need to add to the current value of max WAL senders because your backups will use an extra 1 or 2 connections. That's all you need to do. And the analog of running PGDump to take this backup is then the new tool from 9.1, which is PG-based backup. It's also a very simple, it's a standard Postgres client command, so it uses the same kind of connection. So you run it, you have the same, dash capital U, tell it what user to use, tell it what directory to put the database in. It does have one feature that can be pretty neat, which is dash capital P gives you a progress indicator. Like if you run a PGDump, you never know if it's going to take 5 minutes or 25 hours. This one will at least tell you approximately how far ahead it is in the process. Might be good for manual runs. You probably don't want it in your nightly jobs, but for long-term ones. And if you're doing a one-off backup, the 11 o'clock last night style backup, you add the parameter -x. That's sort of the magic sauce to make that one work. It will generate you a complete data directory, including all the transaction log needed to recover. And by default, it'll generate it in just a plain format. So if you actually point this to the directory called backup, you can actually run pgctl -d backup start. And it will start a Postgres server right in your backup directory. So the idea here is you send these backups to somewhere. Then your backup program might stage this to offsite or anything like that. PG-based backup will just create basically a copy of your data. But it will do so in a way that we guarantee can be restored. It does that by it does require that you have enough transaction logs sitting on your master server so that we can recover by doing crash recovery, basically. If you don't have that, you will get an error from PG-based backup. It'll tell you that your backup doesn't work. So just as usual, remember to check the error codes. Now, the really interesting thing you can do with the physical backups is when you start looking into using log archiving. The main thing here is as we generate transaction log, we send it to an archive, one way or another. And then when we do a restore, we can read it back from the archive. And the transaction log is basically every single change on a physical level that happens in your database. So if we keep every single change, we can go to a base backup, and then we can redo every single change you've ever done, and we will eventually reach the point that you were right before your system crashed. And that's the basics of point-in-time recovery. The point-in-time part comes from the fact that we can also tell the system to stop. So we can say, start from the base backup, keep redoing every change that ever happened, but don't continue past, 10:30 in the morning. because sometime after that, the DBA dropped the important table. So you can stop right before he dropped that table. And that's the really neat part about this one. Log archiving in Postgres is not super hard to do, but it is a lot of manual work. Basically, there are a couple of commands you set. It's pretty simple. You set archive mode on, which turns on the whole concept of log archiving. You set the archive command to something. There are examples in the documentation. I'm not going to go into the details, but basically, you define your own command that responds to the command of take this file X and store it somewhere under the name Y. And you get to pick how. That's sort of both the good and the bad with it, because you get to make the decision of how, but you also have to make the decision. This can be a simple copy of the file, maybe copy it off stream. For those of you who like do that kind of stuff, send it up to Amazon S3. I have tested, and it actually works. You can post it to Twitter. But after about 15, 16 megabytes worth of it, you'll get banned from Twitter by their automatic spam bots. It's kind of boring, but it does work to restore. And then you create a command when you do restore called restore command, which is just the give me back the file you stored under the name Y and put it over here. So you need to design yourself both sides of these commands. But once you've done that, Postgres will take care of the rest for you. There are some limitations on this one that if you've worked with it before, you know the problem in Postgres is that we work in 16 megabyte segment files. If you ever looked in your pgxlog directory, all files are 16 megabytes. Log archiving will send your 16 megabyte file when it's full. So if you have a very low speed system, it can take a long time before it sends the file. And that means if your system crashes before it sends the file, you can't restore it. So you lose data. For that, we have something called archive timeout, which tells it, send the data even if the file isn't full, which would be great, except we still send 16 megabytes worth of file. So if you set, archive timeout to 5 seconds, because then you will only lose 5 seconds worth of data, you just flooded your archive with 16 megabytes every 5 seconds, even if you have no activity in your database. So it's sort of you need to choose one, none of them is good. We solved this problem in Postgres 9.2 with a new tool called PGReceiveXlog that uses the replication protocol to stream. So instead of copying 16 megabyte blocks, we actually copy byte by byte as the transaction log is being generated into your log archive. It makes it a little bit more complicated, but it lets you work around this problem. But the base idea is still the same. We start from the base backup. We roll forward through the log archive that exists somewhere, somehow. And then we return to reality, so to speak. Now, running base backups for this point-in-time recovery is actually very simple again as of 9.1. Run PG base backup. Don't include the flag -x that I mentioned earlier. If you don't include the flag -x, you generate a base backup that's used for point-in-time recovery together with a log archive. If you include the -x, you don't. So remove the -x, standard PG base backup will actually generate just that. If you are on Postgres before 9.1, we don't have PG base backup. So you create and run a manual base backup by calling an SQL function, PG start backup, doing your own base backup, and calling PG stop backup. There are still reasons to do this in 9.1 and later. For example, to assess performance impacts. Like if you want to do that. If you want to use a different way. Like if you just want to tar the file, copy the files over using CP or tar, then you might as well use PG-based backup because that's what PG-based backup does. But if you might want to use rsync, you can use a SAN snapshot here, and it's no longer required that it's atomic across all devices, as long as you run start backup first and stop backups later. Then it doesn't matter. Important note about these. Check the error codes at every stage. Right? If either one of these steps give you an error, your backup is unusable. Another advantage of PG-based backup there is it centralizes it to one thing, but you obviously still need to check the error codes from PG-based backup, because these are still your backups. The impacts from PG-based backup are in a way the same that you're seeing for PGDump, just lower when it comes to I/O, but it will read all your data. So it will generate a lot of I/O on your system. There's really no way of not reading your data if we're going to back your data up. It will be sequentially reading. It will be able to efficiently use read ahead in your operating system and all these things, but it does have to read the data. PG-based backup is single-threaded. It's probably a good thing, because otherwise you can very rapidly kill the I/O system of your server. But it will do over a single thread. So again, if you need multi-threaded backup of some kind, you need to use the manual method and then figure out yourself how to get the files over there. We can do compression again. It works the same way as with PGDump. The compression lives in PG-based backup, not in the server. We can use it here as well by setting a high level of compression. We'll throttle the I/O, make the whole thing take a little bit longer, but have a lower impact on your system. So all of those things apply here as well. Restore performance from physical backups tend to depend on what we call distance to base backup. So you can take a base backup. In fact, you can take a base backup when you install your server and you never have to do it again. But if you then want to restore to something that happened 2 years later, you will be redoing every single database operation that you've done for 2 years. That will not be fast, unless you have a very, very low activity database. So for this reason, what we do is we read back all the log files and we redo all the changes. So it will be random writes. It'll be exactly the same kind of random writes that you had when you created the operations in the first place, but it's also single-threaded, which is something we hope someone's going to fix at some point. That's pretty hard, but it will be single-threaded. So you might actually have slower performance to restore than you had to make the original changes. This is why you'll likely want multiple generations of base backups, and you'll need to do some performance measurements and some checks to see exactly how often. A typical one is you have a base backup every night. Then in the worst case, you have to redo 24 hours worth of transactions. And the only way to figure out how long that's going to take is to measure it on your own system. There's no way to just figure that out. Some people need to run base backups more often than once a day, simply because restore takes too long. That's something you'll have to measure. So I was actually supposed to talk about backup strategies and not how to actually do it. So let's see if we can get back to that. Most important backup strategy ever, please make backups. The number of times that I get called to, I guess future clients, they call up and say, we had a database crash. Can you come help us recover? They're like, well, sure, I know how to restore from backup. They're like, yeah, we don't really have any backups. Like, you don't want to be in that position. Make your backups. That's number one. How to do the backups is you definitely want to do online physical backups in almost every case. You probably want to do with log archiving that lets you do point-in-time recovery. There are a lot of scenarios where you don't need that, right? But you're probably going to need that. The only thing that can decide whether you need it or not is, of course, your business requirements at some point. And you probably want to do a PGDump as well, if you can afford it. Right? If your database is large, you won't be able to afford doing regular PGDumps. But it's probably not a bad idea if you're doing like a base backup every day and log archiving, then run maybe a PGDump every week. It solves kind of a different problem. If you get a disk corruption, that will sort of get included in your backups. Another nice sort of bonus effect of running a PGDump every now and then is it actually reads all your data. So if you have corruption, you'll find out sooner rather than later. It still sucks when you have corruption, but knowing about it is better than not knowing about it. When it comes to backup retention, again, unfortunately, it comes back down to business requirements. And we all know how good it is to go ask senior management, like, what kind of backup retentions do we need? And try to get a useful answer. That usually doesn't happen. But it comes back to things like, how far back does it actually make sense to restore data? Like, if you keep backups for 5 years, if you have to restore something that's 5 years ago in your database, does that even matter? Like, does that data have any worth at all? That'll depend on your data. And sometimes it does. In a lot of cases, I know people who say, if it's over a week old, I might as well throw it away. doesn't make sense to ever restore it. These are the things you need to consider when you're doing this. And at what resolutions? So we need point-in-time recovery up to the second for the first week. But at some point, maybe we reach where we can say, it's enough if I can restore with the granularity of 1 week. Do you need sub-second granularity 3 years ago? Probably not. You probably can't even have someone tell you with sub-second granularity when a problem happened 3 years ago. So those are the things that we need to consider. When we're doing this with the log archiving, it means to do a restore, we require a base backup, every single log file created since this base backup with no holes. Okay, if you're missing a single file, you can't restore past that point. There's no way to get past that. So your strategies are basically you can keep fewer base backups and all logs. Or you can keep fewer logs and more base backups. And you'll have to pick one depending on what your system is. If you have a high velocity system that generates a lot of transaction log, keeping more base backups and fewer logs will actually take less disk space. Whereas if it's a slow speed system, keeping logs is cheaper. So it'll, again, unfortunately, always depend on what you're doing. And in the discussion of backup versus replication, we're still in, you probably want both of them, right? But if you're going to have just one of them, backup's the important one. Replication helps you with hardware failure and pretty much nothing else. And it allows for much shorter service interruption, right? A backup will also help you with a hardware failure. But it'll take you much longer to get back up and running on the other side. But replication will not help you at all with things like the DBA dropped the wrong table, or the application bugged and forgot to add a where statement to the delete statement, things like that. There is an interesting combination that you can make between this, which is lag behind replicas. Right? If your restores take too long, using file-based replication, you can introduce an artificial delay in your replication. So you can, for example, make sure that your replica runs an hour behind production, or 12 hours behind production. If it runs an hour behind production, you have a 1 hour window during which you can actually fail over to the replica without having to restore your data, even if it's the kind of thing that dropped your whole database. If you find it out quickly enough, you can switch over to the delayed replica instead of having to restore from backups. So far, I don't think there are any tools out there that'll let you do this on the streaming replication. But with file-based replication, it's trivial to do this because we're just copying files. We'll just have to make sure the file copying is 1 hour behind. And if you are using a 1 hour behind replica, being less than 5 seconds behind is not really an issue. Another thing that's pretty good when you're thinking about your backup strategies is test your backups. How many people in here regularly test your backups? Like not just did it once. Yeah, that's what I thought. That's like 3 people in the room. Because we all know we should and we seldom do, right? That's reality. But really, you should do it. I have a client, I usually use that during my training as a good example. They had their DBA come in and test their backups every morning. Okay, the first thing he did when he got into the office is restored the backup, went to get his coffee, came back, verified that the backup worked. For his company, that made sense. For most companies, it doesn't. In particular, his backup restored in about 15 minutes. So it was about time to go get the coffee, chat with some people in the office, and then verify it. If it takes you 12 hours to restore the backup, doing it every day becomes very expensive. But it also depends on the value of your database. I mean, this guy doesn't actually verify the backups every morning anymore. Well, he kind of does, and he also does it in the afternoon. They now verify twice a day. Because in that company, their database is fairly small. It contains the entire company, right? If their backup doesn't restore, they don't have a job to come back to. It doesn't matter. That's a very extreme position. Like the other extreme is, we tested the backups when they set the system up 5 years ago. I'm sure they still work. I wouldn't go there. A good thing that I tend to do to get around this is use your backups to deploy to staging and development. Meaning, don't make a new copy from the master. Actually use your backups. Don't just run the backups again. And don't automate this. Do it manually, because then you also learn how to do it. As in, do it manually the same way that you would do it if you were actually restoring from backup. That's a cheap way of testing your backups. Yes? Yep. Yeah. I mean, pure backup validation, certainly automate. I mean, if you're using the deploy to dev as your check, then if you automate it, you've actually automated deploy to dev, not restore from backup. So make sure that you test the right thing. I think I'm pretty much like within a few seconds to run over time, so that's what I had. I'd like to thank you all for showing up. Usually I'd like to take time to say, share your own backup horror stories, but I think we need to get out here and make room for the next speaker. So if you have some good backup horror stories, please share them with me later, and maybe I can put them in the next version of this talk. Thank you.